Welcome everyone for the third day of the workshop. I hope it has been productive meeting, and so far I really enjoyed being part of this whole workshop, and I think it's been fantastic experience. So today we'll have a third day, which is going to be half day, so it's going to be short day. So we have a synopsis and a report from the breakout 2 group from yesterday. It's going to be only 30 minutes. So it's going to be very short. So we'll keep that in the schedule. And then they will be followed by session 6 on the future forward-looking session on strategies for observation and modeling. And then we'll have a kind of a fun breakout 3 discussion session. We'll have a Jamboard here. And then just Sam will provide some directions. So I'm pretty sure you got the email from Sam. So we'll have a fun, interactive way of having a breakout discussion. So it'll be fun. And we aim to adjourn by noon. So this is going to be very high-level summary because we only have 30 minutes for the breakout report and the synopsis. So yesterday we had a modeling session and the observation session going over those current capabilities. And I think the most important point here is that still many global climate models that we use do not capture very important aspect of mesoscale Earth interactions. In part, maybe because ocean model resolution has been progressed as we expected 10 years ago, where we're still at 1 degree in the global climate model, like CMIP class models. So I think this really limits our understanding of resolution sensitivity, process understanding of the physics and impacts, as well as the bias that depends on the model resolution as well. And I think a most important point that I took away from Helen's talk was this community effort is probably a very strong community effort is needed to push forward more high resolution model simulation in the CMIP framework, for example. I think as a community, we can speak for it and then suggest a very strong recommendation to the larger climate modeling community why this kind of small scale process is important and has to be captured in the climate model. Emerging data-driven approaches, like we talked about machine learning yesterday, and then process level understanding from the kind of high resolution LES scale models and high resolution regional climate models will be very useful to understand and submeasures and represent these submeasure scale processes in the numerical models, and also improve the general understanding of those processes. Observationally, I think it's still measuring those surface beyond the surface layer in the atmosphere and ocean in the remote regions remains very challenging. The many coastal observatories are in the near shore region where it's more accessible to us, but the remote region in the deep tropics, so in Southern Ocean, in situ observational capabilities has been very limited still. Now we have these emerging new platforms, AUVs and autonomous vehicles that can that enables this coincident and co-located measurements across the Earth's boundary layers. So those are the kind of new capabilities that we're beginning to have, and they will be critical for cross-validation because you deploy different platforms at the same time. You can provide sort of validation of those different platforms in terms of the accuracy and uncertainties. And then we can hopefully reduce the many different sources of errors. And one of the key sources of error in our interest might be the moist physics in the boundary layer, and things like that. Adaptive sampling and data simulation strategy we also talked about. And enhanced spatial temporal sampling is increasing the need for co-located coincident observation of key variables. So I think all this autonomous measurement combined with the traditional maybe ship-based measurement will be very, very useful to increase our accuracy and understanding at the very fine spatial scales. So this is all I have. So I invite, do you have a panel breakout Lee's name here? So if, I don't have the name here, but if you're the lead of the breakout yesterday, step forward to the podium so we can have a sort of, again, short panel discussion. And then we do have virtual participants as well. Then do we have a list of names?
Yes. Can we go back one slide?
Okay,
Here we go.
So Joseph, Amit, Baylor, Aneesh is not here, I guess. And Samantha and Brian, and Aneesh is there, just in time.
And yeah, Samantha's online, and I don't see Brian. Oh, there's Brian.
I'll be just to say I'll be speaking for the virtual because we combined yesterday.
Yes.
Yes, right. Yes.
Okay, I forgot about that. Thank you, Samantha.
Right. So we did have 4 questions, and we'll go again. We have only maybe 25 minutes now, and 4 questions. So I will ask one panel member, each panel leader, just to respond to the question, maybe 1 minute max. And of course, if there's a repeated points, then just overlap and just skip. I think that's fine. So question first, number 1 is how can observational efforts more effectively inform modeling approaches and vice versa? So I'll start with maybe Baylor. Yep.
Sure. Thanks, Hyodae. So we had a wide, this was actually one of the questions we didn't have as much time to talk about. So I will quickly go through this. So we talked a lot about coordinating the retained values and observables, thinking about things like matching the depths of observations and model grid cells where convenient. We talked a lot about OSSEs, and so observation simulation experiments, and how models used before observations can be valuable. And then we talked about the need for large data sets, particularly in RC flux data sets, because we need a lot of averaging essentially to extract useful information. And that's true both in the models and in the observations, but for kind of different reasons. And so we covered that. And then the last piece, which is always a good CLIVAR one, was we wanted to make sure that the funders and the funding streams are available for these kind of collaborative efforts, which at the moment, it's rare that there are things like the climate process teams that require observationalists and modelers to work together. We don't think it's appropriate to do that for all, proposal solicitations, but we think that it's very important to do it sometimes because it's a critical need.
Thank you. Our group did focus on existing observational examples. So there were various campaigns that were mentioned: Peach, Mesobob, Latmix, S-Mode. And then also there exists some Arctic sail drone data set. And there was some very specific examples of things that could be done with them, including using these existing data sets to spin up or set up LES studies, and then the conditions under which those LES and observations agree can then be used to explore the parameter space further. There was a discussion on how to connect the directly measured turbulent fluxes to the sub-mesoscale and how to think about their being sort of different. Of course, we realized that the direct turbulent fluxes and the sub-mesoscale fluxes can have opposite signs. So turbulence inhibits sub-mesoscale. We know this from Peter's LES work, for example. But we need to come up with new kinds of analysis. And there was a suggestion looking at another specific suggestion was looking at the observation examples and partitioning the bias from the measurements, looking at different boundary layer types, and just repeating what the other session said. Hopefully, for analysis of the existing data sets, funding agencies will find value if the community suggests that this is an important exercise. From the existing models, there was appreciation for the talk given by Abigail, for example, using the LLC models and other such models to integrate observational and modeling perspectives. And there are some, it was felt that there are some easy picks that can be done from the existing models.
Thanks. So we discussed about computing budgets across the transition zone, so linking free tropospheric convection to upper ocean processes. There, there's only one or two examples of that being done currently with models. And then another one was about high frequency sampling, which is very important for many diagnostics and models and observations. So we would need co-located and concurrent observations across the interface for high frequency coupling diagnostics, so diurnal or potentially even higher for sub-mesoscale. And then we discussed about momentum flux budget across the transition zone, both local as well as remote influences of momentum transfer. This would be useful, but we recognize there's not enough observations, especially of the wave field from satellite. So there's no ground truth for this yet. Then another topic we discussed was eddy killing and other important processes that need to be investigated. Spatial scales have been explored for eddy killing, but not temporal scales of processes that contribute to eddy killing. Upper ocean current velocities are key for that, but at higher resolution. And subsurface data can be used to compute convergence and divergence, which is also important for eddy killing effects. And yeah, so we also mentioned eddy killing is easy to diagnose from models, but not so from observations because of spatiotemporal sparsity. Another topic was role of salinity for stratification in some regions. This is important to diagnose, but most of the time it's ignored. And then in terms of what data is needed, we recommend that we have a community effort to define variables that need to be saved for key diagnostics on mesoscale, sub-mesoscale air-sea interaction.
Okay, I think we had a nice conversation about the potential for collaborative push and pull between the modelers and the observationalists. Firstly, from the modeling perspective, is to use the observations to explicitly falsify the model. So come up with experiments where going into it, you know that there are certain observational experiments that you can do that explicitly either show the model did well or poorly. And it's important to kind of put that up front, maybe at the proposal stage, because I've seen a lot of instances where maybe the modelers or the observationalists get pulled in after the fact, and there's a lot of momentum that one team or the other has to accomplish the goals that they put in their original proposal. And so it's probably important to get those written down at the beginning phase. The other thing is for the modelers to kind of push the observationalists. Obviously, the models it's much easier to calculate certain variables like vorticity and divergence because you have the whole field. And we've seen in experiments like LatMix and S-mode that there's been a nice push on the observationalist folks to come up with really clever ideas for how to get vorticity and divergence, which have extremely important physical consequences to the ocean dynamics. Something that's easy to get from the model to actually get in the observations and compare with the model to see if the model is realistic. And as just a check on the observations to make sure it's being done in a way that makes physically realistic sense.
Great. Samantha?
Yes, I feel like our group also picked up on this theme of, we kind of talked about the need for these coordinated, coupled data assimilation efforts where we could be collecting OBS and evaluating models to target specific processes, such as, field campaigns and intensive observing periods. And, kind of just noting how data assimilation is helpful in operational weather forecasting. And I think, again, we're just seeing the need for OBS and modelers to be starting from the ground up. We're also just talking about how kind of going in both directions, both OBS and model data can be helpful for informing, minimum resolution of what's needed or minimum sampling needed to resolve specific air-sea processes. It can be helpful before going into a field campaign to have a better understanding. They can also help in understanding the direction of causality and investigating hypotheses. And models, especially to be able to test observing strategies, for example, to understand if some sampling would actually work to calculate some diagnostic that you're trying to do. But also noting in terms of models informing OBS, how global gridded model products, unfortunately, we don't have as many observations to be to get at the seasonality of change, and so we can still use that insight that we get from the models in order to inform regions for targeted observations, and also just provide a sense of information in data sparse regions such as like the Southern Ocean. So those were just sort of the themes that came out.
Right. Thank you so much. These are the really great points. I think informing observation and sampling strategies from model and vice versa, right? I think those are the key, and I think I see some effort in the many funded projects now, like integrating models and observation plan together prior to the field campaign. I think those are the kind of really good approaches that needs to be continued and sustained. We go to the next question, and we try the reverse order. So Samantha, if you don't mind, you can go again for the second question. Is what new analysis of existing observational data and models offer the potential to address gaps and uncertainties?
I think this will be an interesting one to hear. So one theme that came out, you can hear me okay?
Yes, can hear you.
One thing that came out was the use of artificial intelligence and machine learning to help in developing parameterizations and performing that unsupervised learning. It sounds intense, but really it's comparable to like EOF and PCA analysis, where it helps reduce the dimensionality of data and also helps identify things that, can identify higher order relationships and reduce computational constraints and, understand how the network might identify what are the key things that you should be observing or calculating. Another thing we talked about was just synthesizing and contextualizing observational programs with satellite products, just being able to start, coupling those in situ observations at the surface to, the satellites which provide global coverage and how we can maybe fine tune some of these retrievals. And then I think another one that was important was, and this isn't so much how would you analyze it, but organize the data, creating these data repositories of both OBS and models in a cohesive manner, organizing and standardizing these data sets so you can actually compare and calculate statistics. And also, given the push we have in the publishing world, enabling this easier discovery and availability of these data sets, which I think is something that's, with all of these individual projects we have, can be kind of difficult to do.
Thank you, Joseph.
So our big discussion was also about machine learning. We spent the entire time talking about that, and that might be a consistent response across the whole panel. We were very impressed with Abigail's talk on Tuesday, the data-driven approach to sub-mesoscale parameterization. That was a really clever way of coming up with a new parameterization scheme based on building correlations from the machine learning. The only thing that we were kind of concerned about using this approach is in the middle. Sometimes there tends to be a black box. So you put a bunch of data in and things get built based on how the neural network is set up, and something gets spit out. So it's important not only to just, like Abigail did, to verify that you actually get a better result, but maybe even understand more completely how the machine learning algorithm is building these correlations and why maybe the human didn't see it, or that might actually help us go back and understand the theory behind what the correlations were built and come up with better ideas from a human perspective of why the correlations came out the way they did.
Thanks. Yeah, we did spend some time talking about machine learning, but only towards the end. So we mostly talked about underutilized observations that currently exist. So repeated glider transects in different basins, especially in coastal regions. These are underutilized right now. WHOI, the one Jim Edson is leading currently, those platforms are not utilized enough for studying air-sea interaction on meso and sub-mesoscale. IU's sites were another observational platform that was recognized. Coastal HF radar data, which observes surface ocean as well as boundary layer atmospheric variables. They are underutilized apex floats in, like in the Gulf of Mexico, AXPTs and XCTDs that are launched before and after tropical cyclones. So there are many different observational platforms that are used either only for ocean process understanding or atmospheric process understanding, but not air-sea coupling. Those were highlighted. We need more OSCs, observation sensitivity analysis, for various diagnostics and model data assimilation impact studies. We can also do core screening sensitivity experiments with observations, so subsample observations, and study their impact on air-sea interaction compared to the full suite of resolution. And then, yeah, we discussed about machine learning and unsupervised methods for filling gaps, but these still need to be explored for air-sea interaction. Most of the work currently is on either just the ocean or atmospheric parameterization and not air-sea coupling.
We, in addition to the points mentioned, we also talked about how the existing data sets and the existing analysis that we saw from Jim yesterday, the spread around the mean can be looked at in terms of the correlation of U prime, V prime, and the horizontal fluxes. So how, and for both models and observations, if there is the depth of boundary layer information along with the fluxes, that can be useful in gradient and flux interpretation.
Yeah, to avoid going back over some of the retread pieces, I think the key, sorry, I was not speaking to the mic. So to avoid going over, again, the same things, one thing we talked about was the capability to use indirect measurements to get at variables that were hard to measure directly. So a good example was using the wave field to invert for currents. And so that was something that we had a lot of positive discussion around. We were excited about exploring the and exploiting what the increments are, particularly in coupled data assimilation, where that's available, because we don't really understand what the coupled data assimilation refuses to do, and that would be interesting to, that would be another avenue to learn things. We had a discussion about when the mean statistics are dominated by a few outlier events and how we need to make sure that we're respecting the statistical distributions. Examining the statistical distributions in models, even though they're imperfect, can be a way to kind of leverage a few observations to have a deeper meaning that way. We also talked a little bit about quantifying the uncertainty due to interpretation and how important that is. So things like using a multi-analysis ensemble to get a handle on what different approaches, how much that affects the result. And that's not something we always do consistently. And then, of course, we talked about how you need money. So that was also true. In particular, something that Bob Weller used to call the analysis tail after an experiment occurs. So if you go out and you spend 3 years doing something and you have 3-year postdocs, and then the day all the data is on your hard drive, that's the last day of the funding, and now there's nothing to you don't get a chance to look at it. And this is particularly important for open data and transmissibility of information, because what frequently gets left out is good documentation of the data when you upload it at the end of the window. So we want to make sure that postdocs are hired both for the data management aspect, but also to get a crack at interpretation of what it all means, all the stuff that was so hard to get. So it's pennies on the dollars of the observations to do that. That's all.
Right. Move on to the next question.
Just a note, we have 5 minutes.
So we'll speed up. So maximum 1 minute. If it's less than 1 minute, there's even better. Where are the known uncertainties associated with the current method to diagnose and represent the submesoscale air interaction and mesoscale processes? We start with Samantha.
Let me just get my notes right here. So I think one thing we identified as a key source of uncertainty is just the spatial and temporal resolution, and how we need to understand if we're measuring the right scales. to even diagnose mesoscale and submesoscale air sea variability and interaction. And one important point that was brought up was how, with the changing time and space resolutions, how do your subgrid parameterizations change, and how they would need to adapt? And kind of along those lines, what resolution is even required to eliminate the need for parameterizations? Or on the flip side, how high is high enough? We also talked about convective parameterization in atmosphere models and how we have different schemes targeting different scales and features and budgets, and how that becomes a source of error and uncertainty, and how it's resolving, like drizzle, for example. And then there's a dependency of parameterizations on the background stability in terms of there might be different relationships that are occurring in stable versus unstable conditions, and also understanding what are the observations that we can trust, what's the gold standard for comparison. So those are just some of the things that came up.
Thank you. Joseph?
For time, we talked mostly about fine resolution in the climate models, how that will affect the outcome. And then there's been a lot of great work on coupling of the models between the atmosphere and the ocean, but the need to add in that wave component too, and what that means to the final solution.
Yeah, just make 3 points. So one was, how does uncertainty integrate up or upscale to uncertainty on large scale? So uncertainty in submesoscale and mesoscale integrating up, that needs to be understood. Current generation climate models do not represent any mesoscale or submesoscale air-sea interaction. They may have some representation in the individual components in the ocean or atmosphere, but not in the coupling. And then finally, we could use observations to train probabilistic machine learning to get at uncertainty. But for this, we would need Bia's talk to be a reality. We would need everything, everywhere, always, or all at once. Thanks.
So we talked about how the Money-Nabokov similarity theory breaks down when you no longer have homogeneous conditions. And so that violates the assumptions that are used in there. So we do need to think in new ways about how to deal with that. And one approach was suggested in terms of structure functions, but also in terms of different averaging timescales, perhaps making a longer record that can reduce uncertainty. But that also needs directionality of the information where the spatial gradients matter. For both data and models, there's averaging in length and averaging timescales that introduces uncertainty. There was a need to go further on the stochastic part, and there's a piece missing in small scales of both ocean and atmospheric sites. We need large spatial measurements to look at the variability, and need a mix of local response and far field measurements, so need both horizontal and spatial information. And we need multiple one of those 200-meter tall towers further downstream of each other to get that information out.
So we talked a lot about the limitations as well, consistently. So high and low wind speeds, uncertain boundaries for when the Belk formula apply. In a different direction, we talked about event-based analysis as opposed to statistical analysis, and how that would be important, and certain features being understood to be the underlying cause for statistics. And then the last piece, we talked about the challenges of coupled versus uncoupled model tuning. So something may work very, very well in an uncoupled modeling system and then totally fail when you couple it together. And so it's just a known problem that we don't really have a good grasp on how to approach optimization under those conditions.
Great. So the last question will speed up greatly. What are the useful diagnostics to use to compare air-sea coupling in models and observations? For such diagnostics, what variables need to be saved from models and measured from observation? Can we start with Baylor? 30 seconds each group. How about that?
Budgets.
Okay.
Thank you, Baylor. We also need higher order gradients to be saved more often from the models. So diagnostics like Laplacian quantities of temperature, SSH, first and second derivatives, and for observations, correlation of U prime, V prime, and such quantities.
Budgets as well.
But on that point, the main point that we got and quickly is saving the model at much higher output, or maybe even calculating budgets online and saving them. 1 hour seems to be make people, the observationalists happy, and 30 minutes will be better.
Great. Samantha?
Yeah, budgets as well came up, and the increased sampling to have for the frequency of the output. Also talked about, key variables for like air sea flux, bulk air sea flux calculations, including, transfer coefficients and other computed parameters that aren't typically output, but would be useful for diagnosing some of the background calculations that are happening.
Great. Well, thank you so much, panel. I think we are on time, right? So thank you. And then we'll begin with session 6 now. Bella, are you sharing the session? I guess you can stay here. And so Bella and Sarah are the chairs of the session.
So for this, our last session, it was very interesting to think about what exciting future directions would be, and which work would really be sort of forward-looking. Our first speaker is Bia, who's going to talk about everything, everywhere, all at once.
All right. Hello, everyone. So actually, it's a great segue because I'm basically just going to repeat everything that was said a minute ago. But I'm going to present a brief overview of some future strategies for observations and modeling of Earth interactions. And I'd like to start by saying that very little of what I'm going to discuss, it's my own work. It's really a collection of thoughts from the Air-Sea Transition Zone Study Group, the Odyssey and the S-Mode science teams, the Megan Crowney and the OASIS community, and the review paper by Seo et al. That just came out, as well as some of the discussions that we had earlier this week. All right, so how do I do this? There we go. All right, so the need for improved observations and modeling of Earth interactions is something that really the community has been pushing forward in the past couple of years. And by the Air-Sea Transition Zone here, I should say that I'm referring to the region that goes, it encompasses the ocean boundary layer and also all the way to the top of the marine boundary layer. And these efforts are very well illustrated in this schematic figure from Cronin et al. 2022, where there is a collection of all the Ocean Ops 19 papers that had somewhat something to do with Earth interactions. The thing is that if you go pretty much all of these papers at the end, they had a list of recommendations. And if you go back to these papers and you collect all the recommendations, it feels very overwhelming. And we are left with this feeling that really the only way to move forward is if we model and observe everything everywhere all at once. Fortunately, a lot of different groups have been working on making sense of these recommendations and putting forward a strategy for future observations and modeling of Earth interactions in order to improve Earth system parameterizations. So I'm going to focus on two main questions today. First, we're going to do a recap of what we just talked and go over some needs and gaps in the Earth-Sea interaction observations and modeling. And then we're going to look forward and I'm going to discuss a few successful current campaigns and proposed campaigns that focuses on the Earth-Sea transition zone. All right, and to do that, I'm going to borrow the approach that we used in the Earth-Sea transition zone study group. And I'm going to propose that needs and gaps are defined by a combination of processes, scales, and regions. And so if we focus on needs and gaps that arise from processes first, in terms of surface processes, we need to quantify the role of the sea state, more specifically also of meso and sub-mesoscale processes in mediating air sea fluxes. In terms of ocean boundary layer and marine atmospheric boundary layer, we really need to observe the vertical structure as a function of a profile in order to actually make relationships between surface fluxes and flux profiles. In terms of clouds, processes, and precipitations, there are really sparse collocated observations of clouds, precipitation, and other state variables in the air sea transition zone. And then we also need to improve our skill of predicting extremes, such as atmospheric rivers, floods, droughts, and tropical cyclones. And then I'm just going to show a couple research highlights that back up these needs or give support to these needs. So here we're looking at a figure from Ali Cobb's poster, where they looked at the impact of anomalous SST, in this case is the worm blob, on the frequency and intensity of atmospheric rivers. And on the opposite end of the spectrum, here's a figure by Nick Pizzo's poster, and it also appears in Versica et al. 2022, showing the impact of sub-mesoscale ocean currents in modulating the sea state, more specifically wave breaking here. If we now move to needs that arise from scales, this is a schematic figure from the review paper by the working group, and we see that at basin scale, there's really a need to better constrain the effects of the ocean on storms and the storm track and rainfall patterns. At oceanic mesoscale, we need to improve the parameterization of the mesoscale-driven Earth interactions in climate models that do not explicitly resolve mesoscales. And for sub-mesoscales from Lionel's and Lunastock, we've seen, and Jacobs as well, we saw that there's very little that is known from an observational point of view regarding wind and thermal feedbacks at sub-mesoscales. All right, so here we have a figure from a paper by Cicada and Kortman in 2016, where they really emphasize the need for resolving ocean mesoscale in order to have a good assessment of near-term climate predictability. In this case, they focus on the Gulf Stream. And here on the right, it's a figure from Lunastock that we saw earlier this week, really emphasizing the need to look at both current and thermal feedback together. If we now move on to needs from regions, this is a figure from the Megan Cronin Oceanobs review paper, and the black dots are the locations for the oceanside moorings, and we see that the observing system is really heterogeneous currently. More specifically, we see that there is a very large gap at high latitudes, and the trouble here is oftentimes bulk formula do not work, so we need improved flux observations in these regions. Also, for boundary currents, both eastern and western boundary currents, we need to quantify the role of sharp SST gradients in the ocean, in the atmosphere, both locally and remotely. And finally, in the tropics, there is a need for better understanding high-frequency variability. And to illustrate these points here on the left, it's a paper from a review that Mark Barraza led. It appeared on BAMS. And the different colors are different surface flux products. And this figure is showing sensible heat flux. And you see that there is very large discrepancies of surface fluxes in high latitudes. The products just don't agree with each other. And here on the right, it's two examples. One, it's from a paper by Sarah Gilly and collaborators in 25 that shows the amplitude of the diurnal winds. And we see that there is a very strong signal in the tropics. And here on the bottom is some work by Jacob Vinograd and McFadden, looking at the diurnal variability of currents, more specifically of the vertical shear in the tropics. All right, so now that we've established these needs and gaps, how can we move forward? So I'm just gonna show a couple examples of current efforts and forward-looking efforts that are aiming at addressing these gaps that I highlighted. So first I want to talk about S-mode. So S-mode is the sub-mesoscale ocean dynamics experiment. It's a NASA Earth Venture suborbital mission. And it wants to test a hypothesis that sub-mesoscales have a large contribution to the vertical transport of both physical and biological variables. So we already had 2 campaigns, and the 3rd campaign is about to start in a little less than a month. And what's really amazing about S-mode is that although its focus was not originally on RC interactions, we ended up having a lot of RC variables measured as a result from S-mode. So S-mode combines a whole bunch of different platforms, including sail drones, wave gliders, ocean gliders, Lagrangian floats. We have a Doppler scatterometer mounted on one of the airplanes. We have the mass instrument that Luke Lennon talked about yesterday, and we also have hyperspectral cameras from the aircrafts. All right, so what makes me really excited about S-mode is that for a long time, we've been looking at these pictures of very intense vorticity and divergence from modeling. And from Jacob's talk, we saw some of these RC coupling at these scales, but these models are not super well constrained at these scales. And now we can actually observe this. So here on the top, this is a figure from the Doppler scat instrument, which is capable of measuring winds and currents at the same time. And here on the left, it's a snapshot of wind speed. And on the right, we have current vectors overlaid with current speed in the colors. And here on the bottom is the curl of this field, and here is the vorticity. And you see this frontal structure in the currents showing up in the winds. Similarly, we can see current SST coupling here on the bottom. So we're looking at the streamlines from the Doppler scat observed currents overlaid with SST here measured by the MOSES instrument. The PI for this instrument was, well, Maker. Okay, you're. And here it's a figure from Mara's poster, also illustrating this coupling between currents and SST. But now the currents are measured from the DOPVIS instrument that Luke Lennon talked about yesterday. So we also see that every time we have a sharp SST front, that corresponds to a sharp current front as well. And those are really unprecedented measurements. Having this 2D view at some mesoscales, it's something really excited about S-mode. All right, because this is me, I could not talk about waves. And what's really cool about S-mode is that it gives us pretty much the first time that we have a comprehensive view of waves, currents, and winds all at the same time. And so here we're looking at sea surface topography, or SSH, measured from mass. And I'm going to play a little animation. And what mass is doing is that as the airplane is flying, is measuring the SSH in these swaths that have about 500 meters of width and can have several hundreds of kilometers along track. And what you see is that there are very clear the signature of surface waves in the SSH fields at these scales. And here on the right, it's a simulation from wavewatch tree forced by currents. And that was done by Gwendolyn Marshall, who's a postdoc in my group. And you see very sharp gradients in HS in the study regions from S-mode. That's something that we've known from modeling for a long time, but we have never observed these gradients. And so the trouble here is that this is also in a schematic that Luke Lennon showed yesterday. When we approach the meso to submesoscale transition, there's an overlap of processes that can contribute to the gradients in the sea state. In this case, we have wave groups and wave current interactions acting to modulate the wave field at the same scales. And this is really clear here, where you have this continuous swath of mass. You can see these high and lows of wave crests and troughs corresponding to modulations by wave group. My point here is that the wave field is highly heterogeneous. And really, most of the sea state parameterizations consider spatially smooth surface waves. And that's not only true, for significant wave height, but also for other quantities, such as the Stokes drift. So here on the bottom, we're looking at the Stokes drift from a model that was forced without currents, and here with currents. And we see these very sharp spatial gradients in the Stokes drift that arise from wave current interactions. The other thing to note is that in order to properly quantify the Stokes drift and parameterize it in models, we need full directional spectrum. So there's been studies from Lennon and Pizzo showing that if you miss the transition from equilibrium and saturation range, you can grossly underestimate the Stokes drift. And also the directional distribution of the waves will impact the Stokes drift as well. All right, so the next thing that is really exciting is that we're planning to take the technology from Doppler scat of observing currents and winds at the same time and taking that to space in the Odyssey satellite mission concept. So Odyssey, it's a mission concept that PI is Sarah Gilly, and our goal is to measure winds and currents at the same time in a way that it can assess how these two variables evolve at fast time scales and what's the impact of winds and currents to improving weather and climate prediction. I really encourage you to go check more at our website, odyssey.ucsd.edu. And just to give you an idea of what this looks like, here it's a snapshot of velocity from the program of record. It looks like someone forgot their glasses. And that's what Odyssey is going to allow us to see in terms of currents. And then here on the right, it's for winds. The right panel, it's a program of record, and now we're showing gradients. And here, it's what Odyssey is going to enable. I really wanted to give a big shout out to Alex Weintier, who put the Odyssey simulator available on GitHub. I encourage everyone to go there and try to play with Odyssey simulated data. All right, still talking about remote sensing. We have now the capability or potential to observe fluxes, not only momentum fluxes, but heat fluxes from space. Aneesh is going to talk about the butterfly mission concept. And in the European side, there is a mission called Harmony that is actually really clever because it's going to use one existing satellite and with 2 more satellites to observe winds, waves, currents, temperature, and even ice drift all at the same time. From a modeling standpoint, I think we have a very exciting future. We've seen results from this simulation at both LunaStock and LeonelStock. This is a couple GEOS MIT GCM global simulation that has a 4-kilometer ocean and 8-kilometer atmosphere. And there are a couple key points that I wanted to make here. First one is that we need simulations of this kind in order to make OCs and OSCs. But one thing to note is that the uncoupled run has to be forced with consistent atmospheric forcing. Currently, the equivalent uncoupled run that we have for this simulation was forced with atmospheric reanalysis, so we can't really compare them. And this is easier to do at regional scale, but it's a bit more challenging at global scale. So I really think we need to push forward in terms of having a run that we can use either as a digital twin or as a nature run. All right, so now that we've seen what's in the future and also some of the needs and gaps that we have, I just want to echo a vision that really comes from several groups and mostly from OASIS as well. So the idea here to move forward, since we cannot have everything everywhere all at once, would be to have a combination of super sites. This would be heavily instrumented locations. These locations would be chosen based on the needs that arise from the locations, the regions. And then these regions would also be the target for process studies that would inform our models, right? In combination with these super sites, we need a global array of satellites that are capable of measuring fluxes of both momentum and heat, together with an in situ array of flux-enabled moorings. And then that's all combined with this digital twin of the ocean and the atmosphere, or the air-sea transition zone, in such a way that we can use that to do OCs and OSCs to inform the locations of the super sites, and also use these process studies to improve parameterizations that are going to feed back to these models. And then to conclude, if there is like one message that I need, it's really like common, it resonates with everyone, is that we really need an integrated approach. So we need to treat the air-sea transition zone as a unit. And in order to achieve that, I'm just gonna leave these questions here for discussion, but I think that we need somewhat a top to bottom approach coming from the funding agencies. And that's most questions for us to discuss later today. And thank you. Are we doing questions now or later?
Yeah, come back at the end. We have a discussion
Okay.
at the end. So we'll hold questions for Bia as we look at the other pieces. So now we have a sense of what to do when we have some things, some places, some of the time. Anyway, okay, butterfly is next. And Aneesh is going to tell us about that.
Thanks, Baylor. Yeah, thank you, Bia, for introducing this. So I'll be talking about this satellite mission concept called Butterfly. I'll be presenting on behalf of Caroline Clayson, who's our PI, and the entire science team that's been put together. This was proposed previously as a Earth Venture Mission 3 concept to NASA. We reviewed in category 1. We heard it went to the NASA administration for selection, the final pool, and yeah, unfortunately, it did not get selected. But the mission that was selected was in its 3rd round of submission, and this was our 1st round of submission. So we were happy about that, but would have been happier if it was selected. So in terms of motivation for this, yeah, I don't need a lot of motivation for this group, but this is what's upcoming in California. If any of you are traveling to Northern California over the next few days, look out for this winter storm. There's a big winter storm, late season winter storm when the snowpack is already full. So it would have a huge impact in terms of snowpack, but also potential flood and flood watch. And this is our model forecast uncertainty over like a week forecast. So this is from the NCEP GFS. This is the ECMWF atmospheric river, so integrated vapor transport. Long term, there was no real forecast on the 10th of March of making landfall over Northern California. And both models were very different in terms of their forecast. This atmospheric river event, it originated from the tropics, but it's passing over this SST anomaly, warm mesoscale featured SST anomaly, picking up a lot of moisture on the cold side, moving towards the coast. And that's something the models really have a tough time getting at in terms of what influences these winter storms. That's current motivation for what's upcoming and what are the challenges that we need to address. This is a statistical analysis motivation. So what we are seeing here is correlation of unfiltered wind speed and SST. And most of the regions, except a few regions like in the northern Indian Ocean or the coastal upwelling zones, most regions you see this negative correlation where the atmosphere is influencing the ocean or the ocean is responding to atmospheric forcing. So high winds, cool SST, low winds, warm SST, that's the picture we have of the ocean being or responding to the atmosphere, but not feeding back or forcing the atmosphere. But when we look at a different diagnostic, this was, yeah, thanks to Hyodae for putting this together. This is looking at filtered, high-pass filtered wind speed and SST correlations. We see a very different picture that the ocean actually is forcing the atmosphere at these scales, at these spatiotemporal scales on frontal and mesoscales. And that's what we want to get to. Over the last 2 decades, the ocean studies and oceanography has been progressing towards understanding how the ocean is actually forcing the atmosphere and making the atmosphere respond at these scales. And we don't really have observations to validate this. This is a figure, we've seen this a few times now in this workshop put together by the US CLIVAR working group. Again, Hyodae Seo et al. is to blame. This is looking at winter storms passing over these western boundary currents. An example is the Gulf Stream. You have these strong SST fronts. How do they influence the storm track? Do they shift the storm track compared to climatological storm track? There's been a lot of literature that has gone into this analysis over the last couple of decades at least, showing that there are strong air-sea fluxes in these frontal regions where there's strong gradients. And this can influence both convection locally, but also the storm track as it evolves. And and moves across the basin. Most of this analysis is model-based. There's very little observational evidence to show these interactions at these fine spatiotemporal scales. And then talking about observations that we have and how uncertain they are, this is looking at standard deviation of 5 different surface flux products that have been put together. So these surface flux products were developed using some in situ observations, but a lot of model reanalysis data, especially for surface air temperatures, as well as specific humidity measurements that go in from models. And different in situ observations, different satellite products at different spatiotemporal resolutions were blended together to put together these different heat flux products over the last 3-4 decades. And the challenge is there are large uncertainties in regions where you have these frontal scales, mesoscale, eddy activity that happen. And this is just across 5 different heat flux products. So we need lesser uncertainty in these products, better observations that should go into these products. That's talking about variability on short time scales. Thinking about the climate time scales, what's the uncertainty in our products? This is the global water budget, a satellite estimate in the blue, and then another group that put together combining both heat and water budget to make them consistent, put together numbers for the different components of the water budget. Just a key highlight, the biggest uncertainty is in this latent heat flux or evaporation from the ocean into the atmosphere. And the value of this uncertainty is equivalent to the total river runoff or close to or same order of magnitude as the total river runoff globally. So that's a big uncertainty in our latent heat flux and evaporation field. Now looking at trends in the evaporation over the last 4 decades, we have large uncertainty in different products that estimate global evaporation. There's different satellite products that also blend together some reanalysis variables, and we have a large spread amongst them to say, it's hard to say what exactly is the trend from these different satellite-derived evaporation fields. So that's an uncertainty that we need to constrain and get a better handle of, because both it's a big component of the global water cycle, but also the heat budget and the heat cycle of the Earth. And now looking at models that have no satellite data, which is here represented as the ensemble red orbs, they have quite similar trends to each other, but they don't necessarily agree with satellites. So the satellite products have a different estimate of the uncertainty compared to this model-only derived estimates of trends in evaporation. So where is the uncertainty? Is the uncertainty in the satellite products themselves, and are the models right? Or are the models overconfident and the error is more in the models, and the uncertainty in the satellites need to be reduced to understand this? So now that was motivation for, we need better air-sea flux products at higher spatiotemporal resolution, both for weather prediction, but also climate scale understanding of the water cycle as well as heat. In terms of what we need to get at these observations, we have seen this formula again a few times in this meeting. We need the turbulent heat fluxes. So we need accurate sensible heat flux as well as latent heat flux. The variables that we need to observe to estimate these accurately are highlighted in the blue. So we need wind speed, difference in near surface air temperature, as well as SST or sea surface temperature. And we also need the difference in the humidity, the air-sea humidity difference. The other variables in these formulae are constant. So that we have these coefficients that could be estimated better, or uncertainty need to be represented in them. And then the air density is pretty accurate, so we can get that from reanalysis. So the target for Butterfly is to observe these variables that go into the heat flux, turbulent heat flux computation, and to observe them concurrently and coincidentally. So this is showing why we need concurrent and coincident observation of these fields. What's plotted here on the left is estimates from satellite of these different variables that go into latent and sensible heat flux computation. So the humidity difference, temperature difference, wind. The analysis or the satellite estimate is shown in the line with the triangles, and the ship estimate from the CLIMAR campaign is shown in the line with the circles. So we see on average, it's a good estimate, but there are large errors or deviations from the satellite and the ship estimates. On the right-hand side, what you see is if you displace the observations of some of these variables spatially or temporally, so there's a temporal offset, a spatial resolution mismatch between these variables, we get very different estimates for latent heat flux and sensible heat flux. So we need these observations on the same platform, observing them at the same time at the same spatial location. If they are displaced in time or space, we get errors in their estimates. So that's the target or goal for the Butterfly mission. We are aiming to observe the variables that are needed for air-sea fluxes coincidentally and concurrently. The PI is Caroline Clayson, who was featured in Jim's talk yesterday, launching balloons from a ship. She also is an expert on remote sensing. She's the PI. I'm deputy PI. Tony is our project scientist, and the deputy project scientist is Shannon, who have long-term experience in satellite development for different missions. Our science team, many of us are here. Mark, Hyodae, Kelly, who's not here, Sarah, Tom, and Reese. This slide is very dense. I'll not go through the details. Happy to talk offline. Just a couple of key highlights. So the mission is to observe high spatiotemporal scales. It has a smaller footprint compared to the AMSR 2. We'll have multiple microwave channels, near surface sounding channels to get at the surface temperature, wind speed, air temperature, and humidity. The goal is to achieve 20 kilometers spatial resolution if the satellite is observing all of them simultaneously. I'll come to the synergy aspect in a couple of slides. We hope to launch. We hope to launch sometime in the next decade. The timeline is in 2024. There'll be a next Earth Venture mission call, and we are hoping to address that or submit the proposal for that. Our goal is to address 2 of the decadal survey questions at least. So how do spatial variations in surface characteristics modify transfer between domains and thereby influence weather and air quality? I've mentioned about that in terms of motivation. Also determining the degree to which sub 25 kilometer resolution turbulent heat and moisture fluxes influence mid-latitude storm evolution and long-term weather. This is one of our science objectives in our mission. The second objective is on the climate timescales. How will the Earth system respond to changes in air-sea interaction? Our science objective 2 is to balance the global ocean turbulent heat and moisture flux contributions to the energy and water cycles and reduce the uncertainty down within 5%. So why now? Prediction systems are moving towards high resolution coupled ocean atmosphere models. Many of the operational models now are at 10 kilometer resolution, at least in their deterministic forecasts. We don't have high resolution air-sea heat or moisture flux measurements needed to evaluate and improve these models. That's a critical need of the forecasting and modeling community. Butterfly fills this major gap in our knowledge on how small-scale air-sea exchange of heat and moisture affect large-scale weather as well as climate. Some of the synergies in our community efforts, there is CIMER, which is a European mission, a microwave radiometer mission, which is aiming to observe SST at 15 kilometers. Currently, it's in phase B2 with a view to launch in 2027, a 10-year mission. If we are able to have our orbit similar to CIMER, we could leverage their data and get our other variables observed at a higher resolution of 10 kilometers. Bia already mentioned this. We've also seen this other times. The other mission concepts that are in synergy is Harmony, a European mission, Odyssey, which is another mission concept. And then there's also a NASA planetary boundary layer task team that's currently in incubation. Many of the science that is being discussed in this team is also relevant to our mission. You can scan this QR code to go to our website where we have more information about the mission. In terms of ongoing effort, we are developing a satellite simulator. There's plans to have a hackathon, make code available on GitHub. We are also looking to add a couple of qualified individuals to our science team with expertise in socioeconomic research, tool development for butterfly applications, use of scientific data for societal weather and climate solutions. So reach out if you're interested. And finally, Butterfly would be the first satellite mission to simultaneously measure SST, wind, and near-surface air temperature and humidity in order to estimate air-sea turbulent heat fluxes and moisture fluxes at unprecedented spatio-temporal resolution. So thank you.
Thanks, Aneesh. So can we pull up Malcolm remotely? So the next speaker is Malcolm Roberts, who's going to give us a perspective on the present and future capabilities of high-resolution coupled modeling. Malcolm was one of the leads of the high-res-MIP intercomparison and also the Primavera multi-model coupled model high-resolution comparison.
Thank you, Bela. Thank you, everyone. Thank you very much for inviting me. Afternoon from a wet and cold Exeter in the UK. So yeah, so I'm going to tell you a little bit about some modeling efforts that are ongoing, and then maybe some opportunities that might link into some stuff that's been talked here the last few days, maybe opportunities for linking kind of new modeling, new experimental designs to get kind of the information that we want about air-sea interactions. So yeah, so I'm not going to tell you the answer to the impact of the ocean mesoscale on multi-decadal to centennial timescales, but that's kind of what we would like to do over the next few years. And I think we're beginning to be able to run simulations to be able to start to look into this, and I'll say a bit more about that in a minute. And then as you've just been hearing, to link those to the observations that we have or that we might have very soon, to be able to constrain the models, to be able to understand the models and the observations together would be a huge step forward. But there are still many questions about what the most useful kind of model simulations, experimental designs might be, particularly what diagnostics and what data do we need to produce, and how to keep those volumes manageable. Kind of noting earlier, and I completely understand that people want 1 hour, 30-minute outputs, maybe at multiple levels in the atmosphere and the ocean, but at models that try to resolve the sub-mesoscale, that they are enormous amounts of data if you're going to output those from global simulations. So we need to figure out how can we do this in a way that's manageable, and also that we can actually share the data in the community so people actually can get access to the data and do things with it. And then how can we process that data and say to be most efficiently distributed and accessed by the most people possible, and then what other observations might we need? So I think kind of some of the challenges. So kind of climate models need sufficient model resolution, and as kind of Helene was saying and others have said, what does sufficient mean is kind of an open question, but also maybe we probably need better improved model physics for these kind of scales to capture the key processes. We need observations at sufficient space and time scales to constrain the models, again, as we've just seen. Designing these model simulations and the diagnostics and the methods to make this a kind of community effort rather than kind of one model runs one experiment, a different modeling group run a different experiment, so you can't compare the two models, you kind of can't compare and contrast the different outputs. So kind of these are all kind of challenges. I hope that the CMIP6 high-risk MIP was a good first step. So this was, as Helene again mentioned, was a higher resolution model to comparison. We had simulations of atmosphere only and coupled from 1950 to 2050. So they're relatively long simulations, but 17 groups managed to run those experiments. So we kind of had a good participation, despite the fact the simulations were quite long and quite expensive. We had a diagnostic list, which didn't have a huge amount of high frequency diagnostics because, again, that's very expensive. And indeed, people said we need to reduce the diagnostic list for the next stage of high-risk MIP because they found it too much. And so we need to kind of figure out this, this constraint and try and get around this somehow. So this is just to illustrate the kind of resolutions that we're talking about in terms of global coupled climate modeling. So the CMIP6 deck, again, that Helene talked about. So typically the ocean resolutions are mostly order 100 kilometers still, and the atmosphere typically between 100 and 250 kilometers. There are a few that are getting down into the kind of 25 to 50 kilometer, but not so many. And then I say high-risk MIP, the first time in CMIP, we tried to target models to try and get down to the 25 kilometer scales and then even to the kind of 10 kilometer scales as well, and try and analyze and assess the impact of representing those scales on the climate system. And I'll kind of tell you one example of that. Again, Helene kind of touched on this, but this is from an Eddie Rich model. So we did a high-risk MIP simulation with a 25 kilometer atmosphere and a 1/12 degree ocean from that 1950 to 2050. So very short spin up, lots and lots of provisos here. But the one thing the model had going for it is that it had a Gulf Stream separation differently from all of CMIP6. So basically all of the CMIP6 models, the Gulf Stream separation happens too late. It basically is forced off the coast because the coastline's in the way. So those are the colors. The black here is the observations, and the red is this particular high resolution simulation. So the Gulf Stream is wrong, probably as wrong as those other models, but it is wrong at least in a different way. And so we found as we went into the future, as the Atlantic meridional overturning circulation slowed down in the future, the Gulf Stream moved northwards. That gave a 4, 5, 6 degree warming right near the coastline, which produced enhanced precipitation near the coastline. And you can probably see that in a few of the, so this is the highest resolution, a few of the resolutions do get that local impact. But we also found, at least for one ensemble member, that we had a big impact on Northern European rainfall as well. So we had an increase in winter rainfall of kind of 15 to 20% in that one ensemble member, which, as Helene said, was outside the range from the other high-risk MIP simulations, pretty much outside the range from all of the CMIP6 ensemble and the UK climate projections ensemble. So this is a model where you do the Gulf Stream, and at least in a different way from all the other models. And through how that changed in the future, through how the air sea interactions are happening over the Gulf Stream, and through teleconnections of that to other areas, you get an impact which is outside all of the range of the other climate simulations. And so it's indicating a risk here that we don't find in all of those other simulations. And so it kind of indicates that we really need to dig in a bit to higher resolution. What are the kind of things that we might introduce to the models and to the climate projections? So just to say that one ensemble member had a particularly strong variability to give that signal by 2050. We ran 2 further ensemble members. The signal was not nearly as strong, although the Gulf Stream moved in a similar way. So we need a bit of an ensemble. We need higher resolution, and we need to try and kind of tackle some of these biases in the simulations. So kind of how might we do that? So there's a few projects that are trying to do that as global climate models at 10 kilometers and below. There are many others, so not the ones I don't mention here. I know there are many others. You've seen the MIT GCM work this week as well. So I'm just kind of mentioning 3 that I have been involved in. Whoops. So the Next Gems project is trying to do, I think it sounds like similar to that MIT GCM work. So running at kind of sub-mesoscale type space scales and running eventually over decade timescales towards the end of their project. We have a European project called ERIE, which started this year, and that's aiming to do multi-centennial simulations at around 10-kilometer resolution in the atmosphere and the ocean. And also you heard earlier this week the CSM simulations with the 10th degree ocean and the 25-kilometer atmosphere. They have already run basically the full CMIP simulation suite, all of the spin-ups and the 1850 to 2100. So they're kind of the example to follow in terms of having a coupled climate model, multi-centennial timescales with an ocean mesoscale. So it's kind of, we need models to join that so we can kind of look and see which things happen to be quirks of individual models and which things are, you know, kind of robust things as we improve these process representations. So NextGEMS, just very briefly, so there's 2 models in NextGEMS. There's the OpenIFS, so the ECMWF atmosphere, coupled to this FESM ocean unstructured mesh, ocean and sea ice model. And then there's the ICON model. And so they're running at between 2.5 and 5 kilometer resolutions in the atmosphere and the ocean. One figure that Deanne Pudrastahan kindly sent me, so they've been doing some analysis of some initial 5-kilometer coupled simulations that have run a couple of years, and they have diagnosed the vertical mixing mechanism in those simulations, and then looked at the coupling strength as diagnosed from the VMM mechanism. And this is kind of the plot of that coupling strength. So again, as you would expect, the coupling strength is strongest in the boundary currents in the Southern Ocean and elsewhere. But it's just to be the first time that actually looking at this particular mechanism and being able to derive the coupling coefficient, the coupling strength is the first time. And then they can also then look at the kind of spatial scale. So again, they've looked in the tropical Pacific, for example, at tropical instability waves. They've kind of looked at the frequency wave number spectra of the SST and the wind stress divergence. And you can kind of look at the different time scales and different space scales associated with the tropical instability waves. And they've done similar things over the Gulf Stream. So that's just some things that they're beginning to do in terms of atmosphere-ocean interactions. So our ERIE project, which, as I say, started this year, it's 4 years long, and our kind of science question is to better understand the role of the ocean mesoscale in climate. We have 4 models. 3 are going to be running the high-risk MIP experiments, and they're all around trying to go around about 9 kilometers, 10 kilometers in the atmosphere, and between kind of 5 and 10 kilometers in the ocean. And then our model at the Met Office is going to be a little bit lower resolution in the atmosphere, but going to be trying to do the full CMIP6 timescales. So the hundreds of years of spin up and pre-industrial control, and then 1850 to 2100. Now, an issue for us that I'm kind of battling with at the moment with the data request is, if you look at the data volumes of these global models per year without very much of the sub-daily stuff put into that data request, you're talking, you know, 10s to 20s of terabytes per year, per model simulated year, and we're looking to run these for multi-centennial timescales. So the data volumes get huge very quickly. We're trying to do things like automate, so we're trying to think about how we can automate the detection of atmosphere and ideally ocean fronts, atmospheric rivers, tropical cyclones, extratropical cyclones, ocean eddies. Do that in a workflow as the model runs, intercept the data maybe as it's going to storage, and do the tracking to save these features, and then publish just the features directly, as well as publishing the kind of full data sets as much as we can manage. But there's a question of how do we deal with these data volumes? How do we do we have the models that are capable of these kind of scales now and simulations, but how do we figure out the data volumes? And so one suggestion, so we've been having discussions now for a year or so, evolving high-res MIP towards CMIP7. Are there kind of extra experiments that we could suggest, for example, in high-res MIP, as well as long kind of coupled simulations and atmospheric simulations? Can we take a leaf out of projects like the Diamond projects, which have been running kilometer scale and doing kind of shorter, a few, you know, tens of days simulations up to a year of simulation? Are there kind of experiments that we could take from those and add those to high-res MIP as a 1 year long experiment that multiple groups might be able to do? That could mean that groups running at sub-mesoscales might be able to do it as well as the lower resolutions. That could, with a shorter simulation, could allow us to maybe have a wider diagnostic list, and also might give us a framework to test more of these automated production of the metrics that we might be interested in. And then we're also thinking about longer simulations. So, for example, we heard earlier in the week about filtering or kind of smoothing the Gulf Stream. So can we maybe filter out the mesoscale from an SST forcing data set? So can we filter out the eddies or run an atmosphere-only simulation with and without the mesoscale eddies in that forcing, and again try and understand a bit more what the eddies do to the atmosphere. So in summary, I think we, in some sense, I'm not sure I can speak for all the modeling groups, but actually the models now, we have models, they can run at these kind of scales. Yes, we maybe need to develop the physics and things still for these scales, but the models are kind of the easy bit. It's the data volumes, the processing the data, the making the data available that is becoming a massive challenge for these simulations. And so we can figure out the metrics or the key diagnostics or ways of reducing the data volumes that we need to kind of throw around the world. I think that could make a really big contribution. And you know, if we can figure out new experimental designs and things in some of these multi-model campaigns that could maybe also link to the new observational campaigns, then I think again we can make some nice progress. So I'll leave it there. Thank you.
Thank you very much, Malcolm. Bia and Aneesh, if you come back up, we can have a panel discussion and some open discussion. And Malcolm, if you can stay on and keep your camera on, sure, so that we can see you here. You can't tell, but we can see you.
Maybe I could just firstly take that question that Helene passed on to me yesterday. So I think, and the questioner could correct me if I'm wrong, I think it was, how do we figure out what resolution we need to represent these scales properly? I think it's difficult because as we increase the resolution, we change the mean state as well as changing the variability. Maybe some of these kind of experimental designs, we could kind of fix the ocean at whatever resolution we're interested in, and then potentially change the atmosphere. And that might give us some clues as to, you know, how the ocean information gets into the atmosphere. That how you do the coupling might come into that as well, but that could be one thing to do.
So if anyone would like to come up and ask questions while we're waiting, I guess, so we've been talking a lot about both global satellite records, but also a lot of the discussion, this meeting has been about regional observations, you know, both S-mode and other things. To what extent do each of you think that the regional outlooks are linking up with the global outlooks as we think toward climate scale? So that's both regional coupled modeling from Malcolm's perspective, but also, I mean, Bia nicely connected S-mode into the rest of the discussion, but maybe we can get started there.
Scared of my. Baylor, I think I wanted to bring back a comment, and I think that was one of Mome's point maybe in the discussion the first day, which is the challenges in actually absorbing the data from these process studies and feeding that back into the modeling, because just the data is not collected in a way that can be ingested by the models. So I'm not an expert in like data simulation or in the modeling development, but I think it all comes back to the synergy. I don't think when these campaigns are being planned, they're being planned with both components in mind.
I think it's definitely necessary, but I don't think we are there yet in terms of, I mean, one, the regional process studies are looking at small scales, right? To get to mesoscale or sub-mesoscale variability, we need a large region that needs to be observed simultaneously. So we would need a combination of these process studies and regional modeling experiments in a coupled data assimilation framework to put everything together consistently. And we're getting there, like the coupled data assimilation is being developed with strongly coupled data assimilation where the ocean and atmosphere can influence each other. Regional process studies, we've been doing that for a while now, but not focused on mesoscale, sub-mesoscale air-sea interaction. S-mode is getting towards sub-mesoscale, I guess. Yeah, I think it's definitely necessary for validation, calibration of these satellite missions plan, validation of models and improving models or subgrid scale parameterization of models. And the tools are being put together. So hopefully in the next decade, we'll be where we can do this.
How about you, Malcolm? Did you have thoughts along those lines as designing these experiments?
So yeah, I mean, I confess I am a global modeler, so I kind of tend to stick to the global side. And I guess on the larger scales, if you want to look at how, you know, like in my example, how the air-sea interactions might interact on the larger scales, then it's difficult to do that, to pick a region that can both do the local processes and the kind of larger scale impacts. And also then allows you to do global, you can look at the Kuroshio and the Gulf Stream rather than just one or the other.
So thank you. I mean, I'm trying to link together some of the themes that have come up in the workshop over the past few days, and with a forward-looking aspect. I think one of the other key questions has been, I mean, all of these efforts are about getting simultaneous measurements, so simultaneous coupling of atmosphere and ocean rather than separate models, simultaneous observations from satellites or simultaneous in situ observations. So I guess forward looking, I mean, maybe we're getting close to being able to observe bulk formula simultaneously or use bulk formula in a way that numerically makes sense. But what are the challenges as we go forward from that perspective? Is that going to be, are we going to find that the bulk formula are actually not the tools we need? Or, is it that we're going to have, we will close down those questions, but then a whole set of new questions come? I mean, what do you think the prospects are for looking forward after we make that simultaneous, consistent measurement or numerics to happen?
I mean, I guess one challenge, and Bia and I were chatting about this earlier in the workshop, is a people challenge of communities being different in terms of ocean model development versus atmospheric model development. That's reducing as we are going forward. There's more development of coupled models where the communities are engaged from the get-go in terms of thinking about transition layers, thinking about layers that are actually coupling the two fluids. That's one big challenge. I think that's happening grassroots where the community is coming together, but some of the programmatic development is not yet there in terms of funding these efforts or having funds that are combined for the model development, observation development towards this. Another challenge I would say is the coupled data assimilation, which needs observations in both the atmospheric and oceanic boundary layers, not only locally, but spatially and temporally distributed to get at like the error covariances that need to be understood to understand how the observations in the different fluids impact each other. We don't have that anywhere yet, or just a handful sites, but that too just at the surface, nothing through the planetary boundary layer. That's another big challenge I would highlight.
I'm not sure I have much more to add to that, but just like circling back to the point I made before, I think that a big challenge is when it comes to parameterizations, I think they always come as a byproduct. There is a field campaign for a particular process to study, and then you use that data to validate or to modify your parameterizations. There's not an effort to actually go and test the validity, like field campaign dedicated to like developing model parameterization. So especially going back to Aneesh's figures of the fluxes differences, you saw those big blobs at high latitudes. So I don't know how to address that. Like, is it because the bulk formula is not working, or is it because we not have enough measurements? Yeah, but maybe I'm just asking questions and not giving any answers.
Yeah, I mean, I think that's a good point, is that exactly these simultaneous measurements are the kinds of things that will help clarify, is it the bulk formula that's failing, or is it just we don't have the data to test it yet? So, and Malcolm, do you have a take on this?
So I guess a couple of things. So I think as coupled models become NWP, the numerical weather prediction, rather than them just being atmosphere only, I think that's going to help us make progress. I think I kind of note a few times it's been mentioned that we don't tend to have wave models in most coupled climate models as yet. And that does, from certainly what I've heard this week, sounds like that's a real lacking in these models to actually do the interface between the two fluids in a much better way. So that's maybe something we should think about including.
Yeah, I guess just as a closing point on this, I think it's very encouraging that all of these projects have such large science team or inter-institution modeling efforts or hackathon kind of pieces, which I think does get to the lack of human capacity that Aneesh was pointing out. So our first question.
Hi. Hi, Malcolm. It's Alison Cobb here. Really nice talk. It's great to see these, high resolution global models that you're running. And we always tend to talk about horizontal resolution. I was just wondering kind of what decisions are made around vertical resolution, especially when we're looking at kind of small scale processes at the air-sea interface. And if we're not capturing things that are happening at those small vertical scales, if we might miss something that's propagating further into the atmosphere or ocean.
So hi, Alison. Yes. So, I mean, I think for the models, I think in both NextGEMS and ERIE, so at least the ocean resolution is a 1 meter thick at the top, which probably 5 years ago would be amazingly high resolution. Possibly now, as you say, there's maybe things I'm sure that still misses. The atmosphere, I forget how thick the bottom boxes tends to be in the atmosphere, but there are kind of issues with numerics and things, I think, to make that much thinner than it is at the moment. So I'm sure that's true. We've never quite figured out, it's so much harder to change the vertical resolution than it is than the horizontal resolution, that we've never quite figured out how to do that as a comparison, because you change all the parameterizations and you kind of change everything. But I'm sure maybe there's scope for having parameterization of that kind of very close interface, and maybe it feeds into this wave question as well.
Great, thank you.
I had a question, and it's kind of more general, and it's maybe more aimed at Jim Edson, but it came from the discussion right at the beginning to do the bulk fluxes, so coming on from this, and question of whether you need to change the bulk formulae, presence of submesoscale and so on. And I was thinking of the CLIMODE results that he has shown. I don't know if Jim. And you get this very nice match between core and the CLIMODE direct covariance. Now, this is in a region of very high submesoscale variability, but you get a very good match. So why is that? And I think maybe it's just that the scatter is where the submesoscale is having an effect, so that it's not the mean. I'm kind of curious about the fact you got such a good match in such a highly variable and heterogeneous regions.
Can you come up to a mic, Jim? I guess this does touch on a point which goes across a lot of things. So if bulk fluxes are the answer, but the scatter around them is maybe a stochastic process or an unresolved process. We have not talked a lot about how you handle that, but that's definitely something that's on a lot of people's minds. So go ahead, Jim.
Yeah, so first, there is evidence when we go across these very drastic fronts, right? The bulk and the direct covariance, if you look at them as transitioning across the front, they become in equilibrium amazingly quickly with the local air sea temperature difference. So I think that's one reason, it's just physically they adapt, partly because we're so close to the surface compared with other. You couldn't say that, I'll bet you, if you were in an aircraft going over the front. But ships, buoys, you're close enough to the interface, I think, that it's a pretty rapid adjustment. But the other thing that this was mentioned during the panel this morning is that I think there's signal in that the plot that I made of drag coefficient versus wind speed, where in the mean you get really good agreement with core, but that scatter about the mean, there's got to be information in that, and that's what Peter and others were talking about. You look at the difference between the measurement and the core prediction, and then see if you can't relate that to something mesoscale-y, like U prime W V prime, the horizontal exchange. You could try all sorts of things and see if anything, gives some functionality to that difference. And so that's something I'm going to try. But I think there's information in the departure of the turbulent fluxes from the sort of climatological mean that I've developed with core. Right? So,
no, I think that's a good point. And I think that's really relevant to a lot of the kind of forward-looking aspects of what are we trying to explain. There's room to explain a lot of extra stuff. So maybe Yuri, do you want to ask another question?
Yeah, I might shift a little bit the subject, but I think it's related to all the talks today and actually the whole conference. But it's been this discussion about having high resolution data and high resolution modeling and global modeling. And Malcolm pointed out that a big challenge, sometimes even more than running the model, is to make it accessible. And I would like to open the discussion in thinking about solutions about that. I mean, if we should all move to cloud computing, or if what are all the options that we have?
Yeah, does anybody want to comment on data accessibility issues, or maybe data accessibility solutions better than issues? I think we know what the issues are.
I can start. I think there are efforts ongoing, both NASA and NSF, at least in the US, and I'm sure there's also in Europe, about the data volume is increasing exponentially, especially from high resolution models, satellites, and yeah, the data accessibility on the cloud, it's becoming easier. I forget who it was, but there was a talk about some of the data volumes are too large to transfer over the internet, so it's actually easier to drive or fly over with a hard disk to your collaborators than transfer it. But I think what I've heard from the communities and maybe some of the program managers is that the community needs to express this demand as much as possible, so that there is support from the programs to fund these efforts, because it is going to be expensive and likely not something individual PIs can do. It has to happen on an organizational level. So that's something we can recommend from this workshop that we need going forward for both science relevant to the topic that we are discussing, but for other sciences as well, that we need funding for cloud capability and open science data tools to access them and analyze them.
No, I don't have anything to add. I just think we need more support from the top bottom, like at the agency level. And NASA is doing a good job in the sense that, like, if you go out on the field, you're required to submit your data and it ends up in the cloud. But I don't know if you're just one PI and submit a proposal to NSF, I don't know where that data usually goes to the UCSD library. That's where I send my data to, but like
it's up to you to manage your own plan and document it your own way. Yeah, I mean, I think this is one thing that traditionally we haven't worked very effectively with data scientists or computer scientists, largely because we're operating in Fortran, which they don't like. But we're getting beyond that now, and I think that open data access and those kind of pieces are really an opportunity to reach out to those communities, data compression as well, in a way that we haven't before. I think my impression is that they are very eager to participate in the scientific and the social aspects of the work that we're doing, its societal relevance, but they don't really know how to get started. So I'm sure we all have friends to kind of maybe get those balls rolling. All right, Tony, I think you're next.
Thank you. I don't have a question, but I have comments that I would welcome the thoughts from the chair, the panels, and the meeting participants at large. The comment is we emphasize simultaneous measurements, and sometimes we take it for granted. And many of us realize the importance of simultaneous measurement in particular diagnostics that we are looking at. But in the literature, people are using existing measurement. They are not simultaneous to push the envelope and do what they can. So there's a lot of literature on that. So we got to clearly make the case, what is the advantage of simultaneous measurement? For example, what is the big deal in computing wind work with simultaneous wind and currents as opposed to taking, quick scan and a VSO, current to do it. That need to be articulated, need to be a lot more propagation on that to help support the in situ programs. Heat flux, there's a graph that Aneesh showed by offsetting the wind speed from other variable, what is the impact? But the impact on time mean is very minimal. Carroll and Clayson has done it with the mooring data. I've done it with the WHOI model. So for climate model evaluation, the Earth's interaction, the ocean front and atmospheric front. So we need more publications to say that that matters for weathers. And I know Reese Parfit has a lot of thought on that and other people as well. So the bottom line is that we need to have a lot more demonstration that simultaneous measurement matters.
Thank you, Tony. Maybe Malcolm, do you want to respond to that? I think that's related to the event capture style of diagnosis that you were discussing, of the atmospheric river statistics and those sort of things.
Yeah, sorry, so my internet cut out for part of that, but yes, I mean that's what we're trying to do is to I mean, it comes back to the previous question, kind of compress the data. We're trying to produce things that have compressed the data by tracking the atmospheric rivers and other things, and then maybe it becomes easier to look at the interactions with a warm blob or with something else. So yes, I think there are ways perhaps we can be cleverer in producing data sets that could be used in that way.
Yeah. Just a quick comment on that. I think, even climate prediction, it's almost impossible to predict one accurate climate projection in the future. We need uncertainty around our predictions, weather and climate. And so, yeah, just getting the mean right is not enough, and we need to quantify that uncertainty and characterize it. So,
yeah, that's very helpful. MoMA?
Yeah, it's another question for Malcolm, I guess. Touches on what we talked before. So if you go to high-res like in long-term integrations, the stuff gets very redundant in a sense, right? Because you have so much high resolutions and you again produce the same process over and over again, and you just do that to capture all scales at once, right? And so then you get in the data pipeline problem, and I think maybe a third way would be like nested experiments somehow, where you provide larger scale information on different climate scales or in different lead times ahead, and then look what high resolution models do, and then you have way less redundancy in the data. And then to Tony's comment, I think the theory is very pretty much limited at the interface, right? Both communities develop their stuff on both sides, and they somehow borrow concepts. But as Bia said in her talk, there's not really a theory going across. The only people who do that are waves people, and they were interested in the waves itself, not in the fluxes. And I think there's a lot to do.
Yeah, thanks, Malcolm. Malcolm, do you want to comment on nesting and cordex or time slices or however you want to chop that
Yeah,
up.
so I think that there's definitely we maybe need to be cleverer than to try and produce the same diagnostics all the way through a long simulation. If a 1 year or a 10-year time slice of the process would be plenty to understand those. So I think kind of agree with that, and similarly maybe you just need a regional slice of the data rather than doing it globally all the time everywhere, as the title from earlier. So maybe smarter ways. Again, it kind of partly comes back to the data. There's smarter ways of getting the right data out of the models rather than just trying to get everything all the time out of them. And then I know that people have done kind of cleverer things with the model to try and, when you're coupling the atmosphere and the ocean, to suppress some of the information from one to the other to try and understand some of those processes better. So that's possible, but it's really complicated to do. So, yeah.
Yeah, and I think, there are a lot of efforts along those lines outside of US CLIVAR, outside of CMIP, that actually do link up to some of these pieces. So I think part of this is we're not always communicating to who the most natural partners would be. Or, Cordex does this, but they only do it in atmosphere-only models. And so we're kind of missing opportunities when experimental designs conceivably where we could be working and improving the science are happening, but they're happening not with input across all of the necessary partners.
Okay,
I think
so,
Alex.
sorry, we're out of time for the discussion.
Oh, all right.
We also, Aneesh, I encourage you to go online. We had a question about butterfly in the chat, or you could come back here and we can address that.
Oh yeah. So anyway, let's take applause. Thank you very much to our panelists for very nice talks. And Aneesh, why don't you answer that on chat? That's probably easiest. Thank you, everybody. I guess this is our closing science session. We have a break now, and then we'll have the breakout session, the closing, which is a very exciting interactive activity, which will involve walking and thinking and talking. And then we'll have a closed wrap up when that's complete. So enjoy your break.
Okay, so we'll go ahead and get started on the discussions about the breakout questions. So it sounded like everyone had a good time or okay time. So what we're going to do for the breakout discussions is we're going to go question by question, and we're going to get the two leads in each of the rooms and the leads in the virtual on WebEx, and both of those will present their a summary of their key points. So we only have about 20 minutes for this, so if you can just keep it kind of high, or short and sweet, that would be great. So we'll start off with question 1. Is this the right question? Yes. So the two leads for that can come up here on stage, and then are the two leads out on WebEx? Are you there? Okay. I just want to see if they're there.
Yes,
ready.
they are. We're pulling their video up, but Ivy and Malcolm are there.
Okay, cool. All right, so first question, are there specific processes, variables, or geographic regions that should be prioritized for future observations? And we'll start with our in-person panelists first.
Some of the things that came up in terms of processes and variables, direct and bulk fluxes in the presence of inhomogeneity, including sub-mesoscale and maybe different surface wave fields. Some regions of interest and processes, western boundary currents, of course, came up with the related eddy and sub-meso eddy field and weather, and also the Southern Ocean, ACC, and also the sea ice zone, due to the extreme lack of measurements in that region and the extremely dynamic and active region. Some more variables, salinity was emphasized, and also a lack of knowledge of the salinity structure in mesoscale and sub-mesoscale and how that might affect air-sea interaction. A more kind of general comment about regions of interest. There might be where locations of where the coupling coefficients are strong, say between SST and high pass wind, or SST and fluxes, and or regions that affect forecast error. And more variables of interest, precipitation, obviously, and more measurement of state variables in coincident atmosphere and ocean boundary layer. Sea ice came up a few times, and in the melting sea ice conditions and the interaction of melting ice and surface waves came up as something a little known. And a final comment was, can we use models and data assimilation to help us choose regions of interest and maybe relate to where they might be affecting forecast error?
Oh, that was a really nice summary. I think that hits all the points that had stickers on our plot as well, but maybe just add waves to that. But yeah, and of course on the posters, there's more discussion. So I encourage you to go look at them. It's a good one.
Fantastic. Thank you. Ivy and Malcolm, would you like to summarize?
Ivy, do you want to go first?
Okay, yeah, I mean, there was, of course, overlap, maybe more than Southern Ocean, more generally the global South, related to salinity of river plumes and radiation measurements.
So yeah, we had the Arctic and particularly kind of south of Hawaii. Apparently models often have big biases south of Hawaii, so it might be an interesting area to understand model biases. Profiles of wind and dynamics across the transition zone and the gas exchange. And then kind of regions and process Pacific upwelling regions and mixing processes, mixing physics in the ocean, particularly important for biogeochemistry. And the wind work on the general circulation was also something that came up.
Excellent. Thank you. And sorry you didn't get to put any stickers on it. It was quite fun. So I guess that's it for question one. So thank you. And let's actually give a round of applause to each of our leads here. They've worked really hard. So
Thanks to all of you guys. That was
yeah. Well, everyone worked hard, but thank you specifically for both of you. Okay, so let's go on to question two. So can we get the two leads up here for that? And so the question two was, what new observational technologies and model development efforts would address the gaps and uncertainties in current understanding of mesoscale and submesoscale air-sea interactions? And why don't we go ahead and start with our in-person?
Thank you very much for this opportunity and for the people that contributed to the ideas. So the first point that was mentioned is that we might need more measurements of air-sea fluxes and wind speeds on the MIZ, the marginal ice zone, and also of the Polinas. So we're talking about high latitude, some polar region. The second point is about the accessibility, although this was mentioned also before in the workshop in these days. We would like to focus in particular on the regional high resolution models, as because of the resolution, they have the potential of bridging the modeling gap towards what could be useful to compare against the air-sea fluxes observations. And finally, in the question that we were given, there is the word uncertainty. So how to better represent the uncertainties in the air-sea fluxes. And one way could be to use stochastic perturbations techniques within the modeling capabilities to better represent the intrinsic and inherent uncertainty in the turbulent air-sea heat, moisture, and momentum fluxes, and thus providing better guidance both to the users of the forecast or the climate models and the observational community on the sort of uncertainty we might expect from those. Thank you.
Okay, so we have a lot of ideas on these posters, and we just had to pick a few for this presentation. The first thing was both observations and modeling of the transition zone. That includes both observations of vertical profiles in the transition zones of both liquids. Secondly, conceptually, to divide the transition zone into three parts: the boundary layers on each side, and then the mushy layer in between that involves both the wave processes, bubbles, and also addresses some of the validity of the one-dimensional approximations that are being done in the bulk formulas. Let's see what else we have here. That also relates to the modeling. In a coupled models, the calculation of fluxes on each side of the interface are not necessarily consistent. And that calls, again, this is the same sort of transition zone that calls for modeling, coordinated modeling effort, or simply communication between the different centers in the search of better or more optimal choices being made in the calculation of the fluxes and there to reach the consistency. Secondly, assimilation, data assimilation, scale-dependent assimilation, coupled data assimilation, and an investigation of the increments. It's something that was discussed earlier already in the meeting. And thirdly, in terms of the observations, so-called space station of ocean wave ocean observations. So that's basically having a hub, basically a supersite that also serves as a hub, as a home for autonomous vehicles going in and out, being recharged, and aircraft of opportunity program, basically using some of the profiling and remote sensing opportunities that we apply from satellite now equips aircrafts with this. Again, there are other aspects of that. I don't want to shortchange them, but we're limited to three.
That's great. Thank you for the summary. And Ivy and Malcolm, would you like to add?
Ivy, go ahead.
Yeah, again, there was overlap. One additional point is that one could use merchant marine ships as maybe one cheap option if we can equip those.
So a few things from us. So it was suggested that LiDAR platforms can be mounted on, say, buoys and drones, which could allow us to profile the atmosphere better. LES, so large eddy simulations in the ocean, can help to start link the very small processes to the larger scale processes, maybe parameterizations. And then one thing that came up with ocean bathymetry. So we don't really observe the small scales in the ocean, kind of 10 to 15 kilometers in the bathymetry, which can be important for wave breaking. And so I believe that things like sail drones can begin to map the ocean bathymetry.
Wow, I hadn't even thought about that. That's great. So, all right, well, let's give it. Question 2, heads. And then let's go to question 3 and get the leads for those. So question 3 was, what potential observational or modeling opportunities should be considered to support future advancement of mesoscale and submesoscale and frontal-scale air-sea coupling and its impacts on Earth's climate? First.
Yeah, I'll go first. It was a very rich discussion, and so apologies that I'm not going to be able to represent all of it. But our group really took this question to ask what submesoscale processes do have an upscale impact on climate, thinking on the climate impact side. And one of the central things that came out is that there's a need to close budgets from both observations and models, and opportunities to do so, hopefully. And in particular, we focus then saying what we really need and the opportunities we have coming up are co-located observations that allow us to do that. So we're excited about some of these upcoming satellite missions that we've heard about. In situ, we talked about the need for robust, trusted, affordable, uncrewed adaptive systems that can really focus on these features of interest that we think are hotspots for some of these fluxes. going back to the satellites, we talked about the need for global and long timescale observations, so maintaining the existing arrays that we have for in situ observations. On the modeling side, we talked about opportunities to use the parameterizations that we have to perform sensitivity experiments. And given all of the models that we have from different modeling centers, opportunities to use those in a unified framework to really assess processes, in addition to the CMIP focus on climate impacts. And I guess just to sum up, we really talked about, for a lot of processes, mesoscale and submesoscale probably are noise, but thinking broadly about what impacts might be on these global and climate scales. So focus on air-sea carbon flux as one potentially important process in biogeochemistry. I'm thinking about weather and extreme event distributions, and yeah, just thinking opportunity to look at different diagnostics of what impact the submesoscale might have.
So we it's sort of same caveats, but we had an interesting discussion in front of our posters, and I think for whatever reason we tended to come from the small scale to the mesoscale in our discussions, and just a few things that came out, and we've heard this a number of times now, is mobile supersites, and it was mentioned, and Nicholas said this too, is that we need to improve docking stations if we want these things to be autonomous. And we want to have AUVs that do missions. They have to be able to come back routinely and reliably in charge. And we don't have that yet. It's an important consideration. I also think that we talked a bit about remote sensing and not satellite and upward looking, obviously. And we're starting to see progress in actually designing these platforms for air-sea interaction and marine boundary layer research. And I think that has to continue. And so butterfly being sort of the classic example here, but other things like dial lidars, so that you're getting profiles of humidity and not just temperature, for example. So there's those are all in the works and coming along. And then just so we talked a little bit about regions. So coupled models and with well instrumented regional sites, and in particular because of the sort of frontal scale focus of this workshop is regions where there's frequent storm passages. It's kind of a no-brainer, but that's what we want to do. And that becomes sort of this event scale sort of process studies that I think we really need to understand the mesoscale. Everyone loves scale-aware parameterizations. It was pointed out, one of my pet peeves, as you've heard, is it's best to use stress, the stress vector, rather than the wind vector when appropriate in our diagnostic studies. We like this. We love this idea of a hierarchy of community models that people can use. And let's see, I'm using those models, Aussies, using those models for observational system design. When you only have so much money, you want to design those measurement arrays so you get the most bang for the buck, and using models is often the way to do that best. And then here's another pet peeve of mine. I put lots of stickers on my own thoughts, of course. The use of state-of-the-art flux parameterizations in climate models. Don't rely on a flux coupler that does not give you realistic fluxes. If you use a state-of-the-art model that gives you realistic fluxes, and if your model blows up somewhere else, fix it. It's not the fluxes are the problem. So I would like to see the community moving more towards that. And I think that is just about it. And I'm sorry if I've missed any of the highlights, but it was not easy doing this. So
yeah,
thanks.
well, thank you so much for doing that. And Ivy and Malcolm?
Ivy?
Malcolm, you start. I meant to say this time.
Yeah.
Okay, right. So the Calval period when satellites go up might be a useful window, given the modeling that often goes on at the same time. Supersites as well, so good temporal and spatial resolution and observations of both the atmosphere and the ocean. Kind of mentioned that every existing platform might be an opportunity to add new instruments to it. And then coastal weather buoys, so they often get damaged by fishermen or whoever else, but there's the potential there. They're mostly for atmosphere, but they, you could potentially add ocean or surface observations to those, and they could become even more useful. That's, I think, the other things were mentioned.
Okay, so we focused on the climate aspect in this question because we thought it was similar to 2 otherwise. So, and similar to before, what we've heard. So closing budgets, assessing regions of storm passages, so where you have cyclogenesis and downstream precipitation, and improving flux parameterizations or making them consistent.
All right, wonderful. Thank you guys very much. And let's give a hand to our leads. Thank you guys very much. And last but not least, we had question 4. And so this question, can data accessibility be improved? And if so, how? Are there any significant improvements to research and monitoring that could result from such improvements?
Hi, so I've already looked at Hyodae's results, and it seems like the common theme is to have some central platform where all the data in situ and model data is all there and accessible using the same kind of system. There was talk about the AWS cloud, and that is a good kind of system, but I think we don't want to have a private company because there's lots of risks associated with pricing and if anything ever goes down there. So to have some kind of community-based common platform, and on that, it would be great to have the ability to do some analysis, whether it's just preliminary analysis before you decide to download the whole data set, or whether it's doing all of your analysis there and just pulling back your figures. And in that framework, we would have the ability to share code, so everyone's not reinventing the wheel each time they want to do some analysis, and also have saved derived products, so climatologies, fluxes, etc. So it's much easier to get the data that you need without kind of replicating what someone else has already done. So as I said, you're having your own version that's not commercial, being able to easily subset data on that system. And one thing with this kind of community platform is to make sure that there's equitable access to people, especially in the global south. So that's the main point that I think both our groups saw. And secondly, having better documentation and metadata, having some kind of best practice and standardized system, and making sure that data sets are maintained. Thirdly, having a catalog of existing data that's already out there. I think a few of us sometimes find a new data set that we didn't know was there and we've been seeking for the past few years. So being able to list and have that catalog of all the data that we already have and make that easy to access. And then at the programmatic level, we think it's important to have support to run analysis on data that we already have. So instead of always having to sell, we're going to do all these new model runs or have this observational campaign, we can say there is this data set and we just want to analyze it. So that would be a really useful thing instead of just wasting the data that's already out there. And then finally, again, at the program level, having support for this kind of common platform and employing people who can do this work, data scientists, data librarians, and making sure there's some kind of longevity to this process.
Yeah, so I guess some unique point that we discussed in our group was given this massive challenge for the modeling centers to provide the large data set, especially high frequency, high covariance term set, that native grids. I think you can think of sort of IOP equivalent for the model simulation where you can subsample, choose the area like Gulf Stream, Crozier, all those high energetics area, and then produce all the output for a short period of time. You don't need a centennial scale covariance terms for whole grid points. So I guess we could think of those kind of shorter term simulations and then save the outputs and then use that for process study that go along with kind of observational analysis or other high resolution simulations. So I think that could be one way to mitigate these challenges met by both modeling centers and also user community. Another side is this the data compressibility. I think we focus on technical aspects. So I think we can still produce large output as long as you improve the data compressibility and transferability. So that's more like computing, software engineering, computing science, which are improving very rapidly. So I guess at some point we'll be able to more easily exchange the data, even though they are very large output size by nature. So I think there's some hope about more equitable data access and more shareable access to those outputs on improved data platform, exchange platforms.
Excellent, thank you. Okay. Malcolm and Ivy? Yeah.
I'll jump in again. So I kind of echo Alison's point about organizing existing data, that we're probably wasting a lot of effort kind of repeating mistakes that already been made or data that's already existing. So really kind of organizing that in a better way. So I think an example for observational data, I think, was ERDAP. So sail drone data is trying to being put in the same place. And then ideally you'd then somehow construct something that you could look at a given time or space point across a bunch of data sets. So you could kind of compare the data easily. Some examples, so NASA occasionally pulls together different satellite data sets into a kind of combined data set. So that might be an example of one way of doing it. And then it was noted that maybe some of the European data archives like Copernicus and ERA5 are kind of you know, are good examples of bringing the data into one place. Okay.
Okay, so our discussion also revolved a lot around cloud-based solutions to pre-process data and also to make it more accessible to a larger group of researchers. One example could be Pangeo, the Pangeo effort. And then also that data is not findable necessarily. So catalog sounds great. And but I mean, this is then the great ideal world. So until then, we need certainly also communication between the different communities, such as modelers and satellite people who have this knowledge, what variables mean what, and also what the uncertainties are and how you can use the data.
All right, fantastic. Thank you all for your summary. So let's give a round of applause. Thank you. Again. So now, actually, now is time to close our workshop. So it's 11:30. And for one thing, we want to thank our sponsors for US CLIVAR, NASA, NOAA, NSF, and DOE for sponsoring our workshop. And I would also like to thank very much Mike Patterson and Sam Coakley for running the workshop and making it so easy for us. So let's give them a big round of applause, especially Sam here. Would you like to take a bow? We'll give you some stickers. And I also want to thank the Science Organizing Committee for the workshop, and their names were up here at some point in time, but you've seen them up before. So they've all of us together, you know, worked to put this together, and we just want to thank all of you for coming out and for making this such a great success as well, and for your participation and openness, and so we really appreciate that. So let's give you all a round of applause for that. And before Sam goes, I just want to real quick, I want to reiterate our desired workshop outcomes. So we had a great time, did a lot of science, exchanged a lot of ideas, and so everything we've done has been recorded. There's been a lot of notes taken, and so in the next couple months, we're going to endeavor to create a workshop report, and we're going to try to do so within the next couple months while the information is still fresh. So there'll be a workshop report that'll be submitted through CLIVAR. And then we also intend to write a workshop paper through BAMS as well. And the idea here is that a lot of these ideas, recommendations, maybe community consensus that we could try to come to will be in a place that you can reference it for the purposes you need to. So there's a lot of different, a lot of different information that people have been digesting here, and some potential outcomes that people can go away from this workshop and work on. And so that will be a main goal of our deliberations in the next couple of months in writing these papers. So let's see. And yeah, so that's the main outcome I wanted to talk about. So if Sam, would you like to Any logistical things?
Yes, yeah, I just wanted to add to the thank you list. Sorry to keep the gratefulness train going, but I want to thank also the virtual participants who weren't explicitly called out, but most especially the people who, it's like 8 p.m. right now. So you are very dedicated, and I appreciate you coming out and participating in the breakout discussions. I also want to thank the UCAR multimedia team, Kelvin and Jesse and Reed, who's not here, but he was here yesterday. So a big round of applause for them, please. Especially if you had a video in your presentation. Stuff is hard. I also wanted to say, I don't know if she can hear it, but thank you to Jessica Martinez, our meeting planner, who, if you got travel support, booked your hotel, she made sure that we had a roof over our heads while we talked about science. So a big round of applause for her too. I don't know if she can hear it, but that's all for me. Thank you.
And so the workshop is adjourned, and safe travels back home. And it was great to see you online as well. And I hope to see you again at a meeting very soon. So thank you all.
Very much.
And